So good afternoon. You are welcome to the third week of the facilitations. I hope you all you are all following us. So last week we started a discussion on dielectric properties of solid. So we continue from where we stopped last week and also try to complete discussion on dielectric properties of solid. So that by next week we start magnetism. Now we go straight. So, as I was saying, we stopped here last week. So we are at the point of trying to define what polarization P is. So with the note I sent to you earlier on, we said that the polarization P is defined as the dipole moment per unit volume, average over the volume of a cell. So the total dipole moment is defined as this. So equation 1.16 is the definition for the total dipole moment of a system. So now we say that let us imagine that a small sphere is cut out of the specimen around the reference point. Then E1, which is now the field, the electric field, is the field of the polarization charges on the inside of the cavity left by the sphere. And E2 is the field of the atoms within the cavity. So there are two fields now, E1 and E2. E1 is the field of polarization charges, which is inside the cavity left by the sphere. And the second one, which is E2, is the field of the atom within the cavity. So now the polarization charges on the outer surface of the specimen produce the depolarization field, which is the third field now. So the depolarization field is opposite to P. That is, the field E3 is called depolarization field because within the body it tends to oppose the applied field E0 as in figure 1.2. If you look at figure 1.2, you will see that we have E0 and EDP and the P. For example, you look at the sphere part, you will see that we have on one side we have the negative charges and the other side we have the positive charges. And now we have E0, which is the applied field across this. So you see that the depolarization field now, EDP, is in opposite direction to the P itself. So if you look at also the cylinder, the same thing apply. That is, the applied field, which is E0, is going in opposite direction to the EDP. So the total electric field, which we define as ELOC at any atom of any atom, not at is of any atom of the dielectric, may be written as ELOC is equals to E0, that is the total field now. E0 plus E1 plus E2 plus E, because these are the field acting within a given atom. So the composition of E1 plus E2 plus E3 is the total effect at one atom of the dipole. So if you measure it in CGS unit now, it will be E1 plus E2, excuse me, E1 plus E2 plus E3, which is defined as this. You know, we have defined that from here now. This is E. So if you bring in this now, we have this expression, E1, which is this. Is anybody asking a question there? Okay. Somebody said he cannot. Okay, that means you cannot hear me. Okay. Can you hear now? But Paul, you have to mute yourself. Saliu, Ismail, you have to mute yourself so that your speaker noise will not interfere with us. Please mute your mic. Is that taken? Okay. So now, if you now rewrite this expression in SI unit, which is the standard international units we are using, E1 plus E2, E plus E3, we have this expression. The only thing that comes into this is just that we introduce 1 over 4 pi epsilon naught, which is equation 1.18b. So now this is the figure we are referring to. Like I was saying you the other time, there are two charges here, the negative and the positive charge, while you have the E naught, which is the applied field, and EDP, which is the polarization field, and this is the polarization, is in opposite direction to this. The same thing in the rod, you have something like this. So now, for these procedures, if you use Lorentz approach, we can derive a different expression. So Lorentz showed that the field E1, due to the polarization charges on the surface, formed a continuous distribution. So the density of the surface charge is equal to P cos theta. P here is polarization, where theta is the polar angle along the direction of polarization. So if you look at this now, if you cut this region now, so this angle is angle theta. So now, if you use that procedures to solve for this expression now, which is the radius, how here is the radius, then because we are in the polar coordinate now, this expression is coming from polar coordinate. So if you try to integrate from 0 to pi now, that is around 180 degrees. So integration of this expression will give us 4 pi p, this is polarization over what? 3. So that is what Lorentz tried to do. And he said that the field 2, due to the dipoles within the spherical cavity, is the only term that depends on the crystal structure. It can be shown that for a reference site with cubic surroundings in a sphere that E2 is equal to 0, if all the atoms may be replaced by points dipole parallel to each other, that is its own summation. So now, for specimens in the shape of ellipsoid now, oriented with one of the principal axes parallel to the applied field, it can be shown that the polarization field will be parallel to applied field, and uh, the, the field now will now be minus n polarization all over epsilon naught. So the constant n is known as the polarization factor. So if you now have it in three-dimensional, Ps, Py, Pz are the components of the polarization. P refers to the principal axis of an ellipsoid. Then the component of the polarization field are written as this. So this is E3x minus MPx epsilon naught. This is for x, and this is for y, and this is for z. Somebody was calling my attention. What is that? Any question? Any question? Okay, there's no question, we proceed. So now it is expected of you to try and look at these exercises. Try to explain what polarization and depolarization field are, and also what are dielectric. We have discussed this dielectric last week, and today now we just discussed polarization and depolarization field. So define dipole moment. All these terms have been defined in the lectures. So you can see them here. We have polarization defined here. We have discussed something about depolarization around this place. So putting all these things together, you should be able to answer these few questions, and also the dipole moment. We have defined dipole moment also within the lecture. So now let's look at dielectric constant now and polarizability. So now let us now consider the dielectric behavior of molecules now, which have a permanent dipole moment. The dielectric constant epsilon has been defined for isotropic or cubic medium relative to vacuum as this. So epsilon is equal to this, which is displacement, all over E, which is the field, which is now equal to 1 plus P all over epsilon on E, and this is 1 plus psi. So psi in this place is known as electric susceptibility. So now the susceptibility is related to the dielectric constant by this expression. Susceptibility is equal to P over epsilon E. P here is the polarizability. So now which now give us epsilon minus 1. So now there are a few things you need to understand here. If the field is not too large, the strength of the induced dipole moment in an atom I is proportional to the local electric field acting on the dielectric. That is, Pi is directly proportional to this is local field now. The total field, we have discussed this ELOC. We discussed that around this place here, which is local electric field. So polarizability is directly proportional to this now. And this now, more or less like a constant now, is this. So we cannot say that epsilon I is the polarizability and pi is the dipole moment of atom I now. So polarizability has the SI unit of cm squared per V, which can also be written in this form: current, seconds, kilogram, meter, but in more often expressed as polarizability volume with unit of centimeter cube, or in Armstrong, which is equals to 10 to the power of 24 centimeter cube. So polarization of a crystal may be expressed approximately as the product of the polarizability of the atom times the local electric field. That is, it is product of the polarizability then times the local electric. This is the local electric field now, and this is your polarizability. So where Ni is the number per unit volume of atom, that is total numbers of atoms that you have in the system, then electric susceptibility can now be defined as this. So we can say that psi is equal to P over E, which is equal to this over this. So if you combine these equations now and the Lorentz relation that we discussed earlier on, you will have to arrive at this point that P over E is equal to this. So it's what you can just take your pen and try to do addition and subtraction and cancel some terms. It's very straightforward. Then you arrive at this now. So hence, this now, summation of I of Ni epsilon I is alpha I is equal to 3 over 4 pi epsilon minus 1 and epsilon plus 2. So equation 1.25 is known as Clausius-Mosti equation, which expresses the relation between dielectric constant and atomic polarizability. You can calculate the dielectric constant of a various material from the polarizability by the use of the Clausius-Mosti equation. That is, if you are given the epsilon of a particular material, you can be able to determine the polarizability of the material using this equation 1.25. So this equation holds fairly accurately for non-polar substance, but it fails completely in pure polar liquid or solid. So what you should take cognizant of in this expression is that this Clausius-Mosti equation can only work for a non-polar system, but in polar system like liquid and solid, it fails. So let that be in your mind, because somebody can ask you, that is, what is the merit and dismerit of Clausius-Mosti equation? You should know the merit is that it can be used to solve or to compute polarizability of a non-polar substance, but it will never, or it will fail when you use to compute the polarizability of polar liquid or solid. So the total polarizability of an atom, can be separated into 3 parts. So we can separate polarizability of an atom into 3 parts: 1 into electronic part, 2 ionic part, and 3 gravitational. So the electronic contribution arising from the separation of electron share Paul, can you mute your mic? Sound is coming from your side. Can you mute your mic? So as I was saying, so you can calculate the dielectric constant of various materials using Clausius-Mosti equation, but it only works for non-polar substance, but it fails completely for pure polar liquid and solid. So take note of this. So the total polarizability of an atom can be separated into 3 parts. I said this some minutes ago, into electronic, ionic, and orientational. So the electronic contribution arises from the deformation of the electron shell about a nucleus. So the ionic or the atomic contribution comes from displacement and deformation of charge ion with respect to other ions. That is when you displace the atom and you deform them, the ions within the nucleus. Automatically, you should be able to have the ionic contribution. So the orientational or dipolar polarizability arises when the substance is built up of molecules possessing a permanent electric dipole moment. So when you have a complete permanent electric dipole moment, which may be more or less free to change orientation in an applied electric field. So in general, the total polarizability is given by this now. We have, since we are having three contributions, the one coming from dipolar, the one coming from ionic, and the one coming from the electronics. So this, the addition of the three will give you the polarizability of a substance, which is the sum of the polar, dipolar, ionic, electronic polarizability respectively. The electronic contribution is present in any type of substance, but the presence of the other two terms depends on the materials under consideration. Is that taken? Any question? Any question? You have any question? Okay. If there's no question, so let's move to the last topic there now, which is dipole relaxation and dielectric losses. Now, dipole relaxation time is the time interval characterizing the restoration of a disturbed system to its equilibrium configuration. So the relaxation frequency is defined as the reciprocal of the relaxation time. So the orientational contribution to dielectric constant is a major cause to the difference between the low frequency dielectric constant and the high frequency dielectric constant. So the orientational relaxation frequency are strongly dependent on temperature and frequency. So we have this equation now. So what you should take note here is that when we are talking about relaxation, dipole relaxation, there is something that is of importance, which is orientational relaxation, and this is a function of frequencies, which depends on temperature and frequencies. So we have this equation: polarizability is equal to polarizability naught all over 1 plus I omega tau. So omega here is the frequency and tau here is the relaxation time. So where T is known as Debye relaxation time and alpha naught is the static orientational polarizability and omega is the angular frequency. So in liquid, we want to relate this equation now. In liquid, relaxation time for a molecules of radius A can be expressed as this. So this tau here, we can write it like this for a liquid, which is 4 pi, this symbol is known as Stokes law. Then A cube over KT. K is the Boltzmann constant and T is the temperature. A here is the atomic lattice constant. So sometimes referred to as the radius, but in the liquid, it will give you the volume. So in conclusion now, in this unit, we have reviewed the dielectric properties of solids. So this is just what you can read from the notes. And now, summary of what we have discussed so far, last week and this week. Solid material can be divided into two distinct groups of the basis of their behavior under the influence of an external electric field. So we have them as conductor and insulator or dielectrics. So specifically, we discussed dielectric. Now, the next one we discuss also is dipole moment, P, is a vector along the axis of the dipole pointing in direction of minus Q to plus Q and having a magnitude of QD. That's when you find the product is the charge times the distance. Then we have discussed also polarization, which is P, which is defined as dipole moment per unit volume. That is average over the volume of a cell. The total dipole moment is defined as this. Then we also talk about polarization charges on the outer surface of a specimen produce the polarization field. So this polarization field is opposite to P. I explained this some minutes ago. So also we'll talk about local electric field, ELOC, at any atom of the dielectric, so which can be written in this format. And if you try to convert this, this is more or less when you have it in CJS units, but when you take it to SI units, you have this. We discuss this. So for specimen in the shape of ellipsoid now, oriented with one of the principal axes parallel to the applied field, so we can show that the depolarization field will be parallel to applied field and is written as this: E is equal to minus NP over epsilon naught. Mind you, this N and P now, is a function of the position of x, y, and z. We talked much about it here some minutes ago, I think, in this area, this place. So NSPS, this is along the x, NYPY, and this is NZPZ. If you see, these are what is written here in a compact form. This is what is written here in a compact form. So the constant n is known as depolarization factor. So the dielectric constant epsilon has been defined for an isotropic or cubic medium relative to vacuum. When you say something is isotropic, it's directional dependent. So you now have epsilon, which is this displacement over field, is equal to 1 plus this, which is 1 plus psi, and psi is known as electric susceptibility. So also, susceptibility is defined as dielectric constant by this, which is related to dielectric constant, and it gives us this equation. And the last thing there is that if the field is not too large, the strength of the reduced dipole moment in an atom I is proportional to local electric field acting on the dielectric. That is, the polarization or the dipole is equal to alpha ELOC, where alpha is the polarizability and pi is the dipole moment of atom I. So also, we have talked about polarization of the crystals, which can be expressed in this format, and this is in GI, and which is known as Clausen-Motti equation, which I told you that it only works well for non-polar system. But once you have a non-polar liquid or solid, it doesn't work, it fails. So what you need to do is to try to solve this problem. The first problem is that two parallel plates have equal and opposite charge. So, for example, let's say the charge is Q. So it will have minus Q and plus Q. So when the space between the plates is evacuated, the electric field is 1.2 times 10 to the power of 5 volt per meter. So the electric field within the dielectric is this. So we are now have to calculate the induced charge density on the surface of the dielectric. So if you want to do this now, we have defined an expression, an equation in the beginning of the class, so which you can use to solve this problem. The second question is that a parallel plate air capacitor is made up of 0.2 meters squared thin plate and 1 centimeter apart. So it is connected to a 50-volt battery. So what is the charge on each plate? So you're expected to try to solve this problem. And the third problem there is that you have a plate of parallel plate capacitor that are 2 millimeters apart and 5 meters square in area. The plates are in vacuum. So the potential difference is this. Then you have to calculate the magnitude of electric field between the plates. This is straightforward. Just try and lay your hands on it. If you cannot get it correctly, by next week, I will do the solution for you. But try it first. I get me now. If you try it, if you're having problem or issue with it, at least where you're having issue with, when you see the solution, you should be able to say, okay, this is where I'm having an issue. So you'll be able to master the procedure of solving it. So, and also question 4, say find the frequency dependent of the electric polarizability of an electron having a resonant frequency of omega naught, treating the system as a simple harmonic oscillator. So I believe, well, this is a bit technical because we have not discussed something about simple harmonic motor, simple harmonic oscillator in this course, but the problem is talking about simple harmonic oscillator. But nevertheless, it's because of the frequency that is coming, because there is no how we talk about simple harmonic oscillator without talking about the frequency. But you can as well try your luck. Are you getting me now? So the last question is say that calculate the individual dipole moment P of a molecule of carbon tetrachloride given the following data. You are given this information: relative permittivity, density, molecular weight, and field. Then find also the average electron displacement. Please try your best and see if you can actually solve the problem. So, do you have any questions? Because we are through with all the information needed or what you are supposed to discuss as regards to dielectric properties. So by next week, we start something on magnetism. So if you have any question, you are free to ask me. The floor is open. If you have any questions, any questions? Any questions? Okay. If you don't have questions, Please and please. Okay. Somebody want to ask question? Paul, your mic is breaking. So your mic is breaking. It's not audible. I can't hear anything. I'm just hearing sound. So I can't hear you, please. Sorry, Paul, your line is breaking. It's not audible. It's not audible. I'm sorry, I can't hear you. I'm sorry, I can't hear you. Can you type on the chat? Your line is... Type on the chat. I can't hear you. Yes. Paul, you can talk. I see you raising up your hand. Talk, but your mic is breaking. I can't hear you. Paul, talk. I saw you. You raised up your hand. So yeah, talk. Talk. I'm waiting for you, Paul. It's like you have issue with your mic or maybe with the internet because your line is breaking. I can't hear you. Maybe you should drop something on the chat for me to read, then I can respond to you. Okay. Fine, no problem. So no problem. Okay. So if there is no other questions, I think we have to stop the class today. So one more thing is that please try to look at the video of the lecture so that you can go over it again and learn one or two things from what we discussed. So if you have any issue, just try and get back to me. Send an email across to me, then I will surely respond to you. Thank you for coming.